Executing automated tests takes time. And as the systems we test grow in features, often the test suites grow as well, and the time we need to execute our test grows. Often longer than good for the team, because the more time between introducing a bug and finding it with an automated test, the less the value of the test suite. So in the spirit of the name of this conference, how can we accelerate automated testing? How can we quicker find new bugs? And a partial answer to that is test impact analysis, a tool or an analysis technique that selects and sorts tests so that they can very quickly find new bugs. And in this presentation, I want to first outline what test impact analysis is, and what its limitations are, and what its capabilities are. And in the second part, I want to share some research results we did on closed source and open source software. And before I start, although this is a big audience room, please feel free to interrupt me with questions. There's people with microphones that can amplify the question, and this makes it more interactive. So feel free to interrupt me with questions. And it need not be a well-articulated question. It's fine if you just have skepticism or doubt or opinions. This would lighten it up a bit. Since I present my experiences, some words on my background. I hold two jobs. On the one hand, I'm a postdoctoral researcher at the University of Munich, where I supervise research projects and PhD students. And on the other hand, I'm a founder of CQSE, a company that transfers a lot of what we did in research into practice. And I hold those two jobs for a reason, because on the one hand, I want to know what's really interesting to measure. Not only because it's easy to measure, but because it's important to know. And that's why I have that research role. And on the second hand, I want to have impact. Because just because you have a tool that runs every night, nothing gets better. And in the founder role, I learn a lot about how we have to build our analyses in a way that they really improve software, or improve code, or improve testing. Last slide on background. This is a couple of the companies we work for. I have them here to show that we don't limit ourselves to a single domain, or programming language, or organization type. The common denominator of all our customers is that software is important for them, and software quality is important for them. A lot of the companies we work with have long-running test suites. Please raise your hands. Whose tests run longer than 1 hour if you run the longest-running test suites? Who's run longer than 1 day? There's still some hands up. We have a couple of teams we work with whose tests run 3 days, even in 10 machines in parallel. And we have one customer whose tests run 20 days. They take 20 times 24 hours to execute every single test case. And what we observe is that the longer a test suite runs, the less frequently it gets executed. Because obviously you can't wait a day in continuous integration. Often you can't even get 10 or 20 minutes to run tests in continuous integration. And a suite that runs several days often only gets executed once a quarter or once a month. And that adds a lot of accidental complexity, because in that time, since I committed the change that introduced a bug, I did a lot of other things, and I switched a lot of contexts. And the longer the feedback loop between introduction and discovery of a bug, the more accidental complexity. So what can we do to speed up finding new bugs? The basic idea behind test impact analysis is to smartly analyze the data that we can capture during running automated tests. And to show you the data, and thus make test impact analysis more tangible, I use a visualization called Treemap. And let me quickly introduce what a Treemap is. The basic idea of a Treemap is to represent components of a software as rectangles. So each rectangle here stands for a component. The example system here is our own analysis software team scale. And the size of a component is proportional to the size of the component in lines of code. And now I go in one level. Now every small component represents a source file. And one level further, now every rectangle represents a method. And it still holds. The bigger the rectangle in surface area, the longer the corresponding method in lines of code. And what I now want to do is visualize code coverage information using color. Gray means the code is not covered. Green means the code is covered. I guess most of you know code coverage. If you run an entire test suite and have a profiler, that profiler can tell you which code got executed in the test. And this is from running a part of our automated suite. So if any tests cover the method, it's depicted in green, and if not, it's depicted in gray. And what I now want to do is dig into that deeper by looking at every single test case in isolation. What we did was we measured every single test case, and if a single test case executes method, they are depicted in white here, and if not, in gray. And since it's pretty boring to go through thousands of tree maps, I rendered that as an animation. And if a test executes code, it's rendered in white, and then it fades to green. And if we now run our test suite, you see that some tests are pretty local, some tests execute more code, there's some areas that get tested again and again and again, and there's other areas that do not get tested at all. And if we capture that data in a smart way, we can use all of that information to improve the discovery times of new bugs. As a side note, a couple of weeks ago, we took part in a German television program called Founders Award, and the German television sent a film team. And they had the task to make a film about software quality analysis, which is hard to picture on an image. And so these animations, which we did for this presentation, had unexpected fame by showing up in that small documentary all the time. So if you happen to come across that documentary, those Treemap animations are not just for show, they have this real background. Now, if we make a change, and in this example, since we have a program analysis tool that analyzes Java, when a new Java language version comes out, we need to extend our analysis capabilities. In that case, a couple of our colleagues implemented a ticket that supports closures. And we can now take a look at what code changed. Everything that was touched in that ticket, if it existed before, is orange, and if it's new code, it's red. And the colleagues spent 4 days working on that, so we want to know if it works. And if we run our tests, I run the same test suite, you observe the same patterns as before, and if you watch closely, whenever a change gets covered, it stays green. And you watch and watch and watch, and you notice that most of the tests don't cover any of the new changes. And that's no surprise, because they were built for old functionality. And to speed things up here, of the several thousand automated tests we have, only 4 actually cover changed functionality. However, all the other test cases cannot uncover new bugs introduced by that change, because they don't cover the changed code at all. And this optimization potential is what test impact analysis exploits to speed up the discovery of new bugs. And it works in 2 phases. And let me explain that by depicting test cases as circles. In the first step, we select impacted tests. That means we compare which test executes which code actually changed, and then we throw out all the tests that won't execute any new code. This reduces the number of tests we need to run. And in the second step, we sort the tests into such an order that we're most likely to find new bugs quickly. Because if we execute all of these, some might pass, depicted in green, and some might fail, depicted in red. In an ideal world, we would like to execute them like this, because at this point, we know all the test failures. We can't do that, because that's unfortunately undecidable, but we have heuristics that sort these to the front. And our goal is to transform such a picture, where you every single time need to execute your whole test suite, to such a picture where you only have a selection that you actually need to perform, and very quickly get to know if there's a bug inside here. Because here already at the second test case, we can decide that we won't need to ship this build, because it obviously contains at least one bug. Test impact analysis works in 2 phases. In the first phase, we execute every single test case once and automatically capture the code coverage per test case. And as a side note, this not only works for automated tests like unit tests, but it also works for UI tests. This is our Selenium-based UI tests, and this is the code coverage that we capture per test case. And you can, in principle, also use this technique for manual tests. Because the profiler that captures the code coverage, the profiler doesn't care about what the test driver is. If it's a unit test driver, if it's a system test driver like Tosca, or if it's a person executing the test. So in the first phase, we capture the coverage for every single test case. And once that preparation phase is done, in the second case, we integrate, for example, into the continuous integration platform or into the test runner. And whenever a test execution is triggered, we take a look at what changed since the last test execution or since an arbitrary baseline, for example, the last release. And then we perform the selection phase, where we throw out all the unimpacted test cases, and the prioritization phase, and compute a subset of ordered tests, which will very likely find new bugs quickly. There are some limitations. For example, there are some changes that affect all tests. For example, if you change your test environment, for example, from on-premise to cloud, then you probably would want to re-execute all tests to capture fresh test data. Or if you change a test case, we also need to re-execute that to know where it will run. So the basic statement we make is not that you never, ever again will execute some test cases, but that you should have two modes of executing test cases. And the first one, execute impacted tests as quickly as possible, ideally every single continuous integration run, but still do a nightly, or weekly, or monthly re-execute all of the whole test suite. Any clarification questions or opinions on test impact analysis on this point before we go to the research studies? Feel free to raise your hand or just shout the question. I'm going to repeat it. Then let me ask yeah, there's one question.
Hello. I was at the booth as well. I asked this very theoretical question that code coverage is basically code coverage, right? But code coverage and test coverage are two different things, because test is more functional side of how code is executed. So classically, this is ensuring that all the code is covered or not. It does not mean that all the functionality is running properly or not. So how you counter this argument, or is it an argument or not itself?
Your question was, is the difference between code coverage and test coverage? We measure code coverage per test, and that helps us to always choose those tests that find a new bug as quickly as possible. That does not answer the question which other features might not be sufficiently tested. So how good is this in practice? And to evaluate how much of a performance boost you get from test impact analysis, you need a lot of bugs. Because you need bugs to compare how quickly can your whole test suite find them, and how quickly can the impacted test alone find them. And we use loads of bugs to evaluate how well this works. And we use the so-called mutation-based benchmark. That means we downloaded a couple of open source projects and used our own code base. And then we automatically inserted or mutated the code to include bugs. A couple of thousand. And then we ran the entire test suite to see how long it takes to find that new bug with the whole test suite. And we ran test impact analysis to see how much quicker it is. And now, the first question is how many of the bugs we found. And that's not so interesting, because we found all of them. So I'm going to skip that from that presentation. The second question is, how big is the speed up of the selection phase? So which benefit do we get by only executing impacted tests, but by executing all of them? And the answer is that it depends a lot on the system, on the way the tests are built. In the best case, here for the Apache Commons collections, we found the bugs in, on average, 3% of the test execution time. But in the worst case, we didn't have any speed up at all. So the key takeaway from that research study was that how much of a benefit you have by only running the selection phase depends on the project. And if we look closer, it depends on the way the tests are built. If we have systems with isolated tests, where every single test case only executes several or a couple of methods, then there's a high impact of the selection phase, because it's quite likely that if I change a single method or a bunch of methods, that most tests won't execute them. But if we look at system tests, so end-to-end tests, we get a different picture. This is the animation of the Selenium system tests we have. And you see that most of the code gets executed by most of the tests and the other way around. So you get hardly any impact from the selection phase. But in practice, if I'm doing continuous testing, I'm not only interested in finding all failing tests. I might also be interested in how quickly I can find the first failing test. And this is what we looked at in this question. The basic idea into this question was, if I start the test suite and then kill the execution after 1% of the time it takes to execute the entire test suite, or after 2%, 5%, or 10%, how likely will I find that a build contains a bug? And the picture we get here is much more consistent. In the worst case, if we kill test execution after 1% of the time, we found 60% of the candidates contained a bug. And on average, we already found 80% of the faulty builds in 1% of the time. And if you put in more time here, then obviously the discovery rate increases. So at 2%, we already found more than 90% of the builds that contain faults. And this makes us very optimistic that if you spend a small amount of time during continuous integration on the impacted tests, that you can already find a large amount of the bugs that were introduced newly. So to wrap that up, in a preparation phase, we need to execute every single test case to see which test executes which code. And once that's done, we can, whenever you want to execute test cases, for example, during continuous integration, select and sort those that are most likely to find new bugs quickly. And if I take a step back, we basically analyze coverage information. We analyze coverage information, and we analyze version history information. We do that with our tool TeamScale. We have a plugin for Tosca. And we call this type of analysis test intelligence analysis. And I just want to quickly outline other types of analyses we do, because with the data, we can answer more questions than how to more quickly find new bugs. The second area we use it for is called test gap analysis. Here we're most interested in seeing which changes slip through testing untested. This is a Treemap as before. Gray means unchanged since the last release. Red and orange means modified or added since the last release. And only if it's green was the code actually tested. And so the test gap analysis tells you where did your developers make changes they didn't tell you about, so you couldn't test them yet, so that you can make a conscious choice if you want to do some more testing before you ship the code into production. And you can either look at that on a code level, here on the Treemap, or you can look at that on a ticket level. By ticket, I mean anything in Jira or Bugzilla or Redmine that describes a unit of work. And we can trace code changes to tickets and display test coverage on the ticket level, because it's often closer to actual features than the code itself. I'm going to do a short demo on test gap analysis at 5 here in the expo hall. If you want to discuss any of those topics with us, feel free to visit us either after the presentation now or at our booth. And to wrap things up, if I do continuous testing, if I re-execute all tests on every run, it's a very slow strategy, because a lot of the tests don't exercise the modified code. Test impact analysis does two things. It first selects tests that are not impacted and discards them, and then orders the remaining tests in a sequence that can very quickly discover new bugs. In our studies, both in closed and open source systems, both in libraries, business information system, and embedded software, we found that in 1% of the time it takes to execute all tests, we found 80% of the bugs on average, and in 2%, 90% of them. Thanks for your time. That concludes the presentation. We have time left for questions.
You must have the source code. You must have the source code to do this. If you have a service, what you consumed, you have no source code. Then we cannot cover the coverage of the tests.
You mean is this analysis also applicable if you do not have the source code? In principle, yes. It's true, it's easy if we have the source code. But if we don't have the source code, we can, in most cases, still obtain test coverage and also compute differences.
Okay, yes, thank you.
It depends a bit on the language you run, on the platform you run on, and also whether the distributable has been obfuscated or not. But it's typically possible. And what we also noticed is that often, if you test for somebody else, and they don't usually give you the source code, if you have a good reason for that, like for example test gap or test impact analysis, they are often open to providing the source code for these analyses.
Okay, thank you.
Any experience with SAP? Yes, we support these analyses, especially test gap analysis and ticket coverage also for SAP. We have a couple of customers that use that for quite a while now, especially for the manual tests. Thanks for the question.
See, if I have an application which has been developed from scratch as a rewrite, so how will this work out? Because the application will be shipped in an incremental fashion. So every time we'll have to put this, the source code, the analysis has to be, because new methods will be developed. And this will, how will this work out in this such kind of scenario?
How does this work for not rewriting from scratch, but for growing software?
Yeah.
We almost exclusively use it for growing software, because hardly anybody's allowed to write anything from scratch.
Yeah.
And we connect to the version control system and have incremental algorithms that very quickly identify what changed and can aggregate all the coverage from all the different test environments to that.
Okay. And the test which you just mentioned, so what kind of test are you looking at? Is it unit test, system integration test, or acceptance test? Because from a QA perspective, mostly we are developing, acceptance tests cutting across, multiple business processes. So how will this work out?
We look at all different types of tests and attribute them or tag them so that you can decide whether you want to look at only unit tests, or only integration tests, or only acceptance tests, or a combination of them.
Okay.
So we're not limited to a single type of test.
Okay. Thank you.
But usually, for test impact analysis, it's more interesting for the end-to-end test than for the unit tests, because that's those that typically take the longest. So when I said that it takes 3 days for one of our customers to execute all their tests, that's not the unit test, but the end-to-end tests.
Okay. Thank you.
We run out of time. Thanks a lot for the time.